All right. How's it going? Excuse me. I have a challenge for us today from our collaborators down in Nicaragua. So I'm going to explain that in a moment. You guys are looking at me kind of funny. Is there something wrong?
Nothing. I want to know what the challenge is.
Okay, good. I also before we get there, we will get there in a second. I also forgot after last class to post this, but I've now posted a peer feedback, so you can give some just as a participation assignment for you to give some feedback, thoughtful feedback of what you liked, you didn't like about the general presentations you saw last week. I'll kind of aggregate those with my own and give you them all to the class. If you think it's a really mean comment, just assume that's from me, you know. So I'm probably not going to do them verbatim either. I'll probably just say, oh yeah, here's a few things that we saw, we thought about, room for improvement kind of stuff. So just as a way to give each other some feedback, also compliments, all of that. Just do that by Thursday. We'll spend 5-10 minutes on that on Thursday. I've not yet looked at your actual introduction sections yet, but that'll certainly be on my list of things to get back to you within the next couple weeks. Okay, so there's that. The challenge, Brian Peters from Migos contacted me a couple weeks ago. I think I mentioned it. They have a situation where there is a family with a private well, and they don't really have any additional treatment aside from that well. So it's not a deep, it's not a particularly deep well, and so he's collected a few pieces of information here on the state of affairs with the water there. We'll notice there's a few things that we probably would want to check in addition. It's certainly, we can see the bacteria growing, and that's not even I could zoom that in further perhaps. Maybe I'll do that for you in a moment. But clearly it's contaminated, right, biologically. So this is probably hand dug, so it's probably, I don't know, maybe 40 feet deep or something. It's probably, if I were to guess, it's probably like that big around or something, just dug down. And they do have a pump to extract the water. So they have electricity, and they have a pump to pump the water out, which could be very helpful if we design something to, say, use gravity, right? We probably don't want to overload that pump itself and assume that can handle a lot of pressure to send something through. Maybe it could be fine, but maybe a more sustainable solution or more likely to be low hazard on their current equipment, it's that, hey, let's pump it up just a little bit higher and fill a tank and use that tank as a pressurization with gravity, right? So there's some potential options there. But just overall, we can see pH is pretty neutral. That's typical. We have conductivity. We could kind of infer that how salty it is sort of by that, and we'd have to double check. I don't think that's a particularly concerning number there. TDS, total dissolved solids, that seems to me like it's actually kind of high, so maybe that's a potential issue. So maybe my guess here is wrong. Maybe there is a fair bit of dissolved matter. So perhaps something to deal with that. Certainly something to deal with the fecal coliforms would be important. And there's also a question about, is there a bunch of nutrients, right? So is there a bunch of nitrogen? This is going to be strange if this keeps up right now, because as I'm writing, there's a bit of a delay. So it's kind of like if you're writing but you don't see what you write yet. It doesn't normally do that. So I might restart some stuff here in a moment, but I'm going to stick with it for a second. Okay, so maybe nitrogen, phosphorus, how much ammonia is there, how much nitrate might also be good to know. So question marks there. So as a potential task, my handwriting is just going clear out the window. here's a good example of what do we do with a potential problem, right? We see a well, so we say, hey, maybe we'd like to improve that water quality. How bad is it? Is kind of the first question, right? Is it bad? Maybe it's good. Well, fortunately, we've had some data. We can say, yeah, that's probably not very safe to drink in its current state, right? Maybe the groundwater is, and the well is protected enough. Maybe there's a cap on it, so it's perhaps reasonably protected from particulate matter. So maybe it's kind of pre-filtered in a sense. Probably not, but we could assess that. We could check for that. So maybe it's there's potential for just chlorinating it and being fine, right? That's a possibility. At least more so than surface water, which would probably have a lot of particulates and may have a lot more organic matter. So we don't know a lot, so there's a few things we need to ask ourselves. Well, okay, what are the challenges? I think the bacteria here would be number one. Can we do something to treat that? Then another question is, well, how much water do we need to treat? Because there's the well there that's going to be replenishing, but how many people are using this? What's the flow rate? Kind of getting at the design, right? So apparently it's a family of 8 people. It might be 2 families living together, or a family with their grandparents, or some arrangement like that. We're not sure. Maybe it's a plot of land with 2 houses on it. I don't actually know. But there's 8 people apparently using this well water. So I, just as a kind of a blind statement here, I'm saying, well, it would be nice to have a 99.99%, I wrote 99.9% reduction of coliforms. Oh, good. But maybe the right target would be 99.99%. So maybe a 4 log. This was just arbitrary. I'm just like brainstorming, putting some stuff out there. We might ought to check what, let's say, the World Health Organization or the EPA or somebody like that recommends for a unprotected well, adding disinfection. There might be recommendations for that. There might not be. We might just have to say, well, we're trying for less than 1 microbe per 100 milliliters. And each of these, by the way, these plates were from 100 milliliters of water filtered. This is with the Del Agua system that we had in class and we're taking a look at. So each of these plates, they all have colonies on them. You can see the pink showed up. Some of these, the pink ones, we're probably not as worried about. The yellow ones then are the concern. And clearly there's, you could stare at that for a little while and maybe count them. There's probably something like 200 or so on each plate, right? And by the way, when I count these in the lab, typically what I'll do is if I have like the clear Petri dishes with the cover, I'll probably actually just count and take a marker and mark them as I count. It's a little harder when you have these situations where you can't do that, but the grids can kind of help with that. So anyway, we have a bunch of E. coli. We know that's a problem. We're going to try to treat it. There's also a question of, well, how much water does each person need? So I took a look briefly to the World Health Organization guidelines, or found a website that was citing them. And I said 30 liters per day would probably be a nice estimate. Kind of the very minimum that you need, let's say, of a disaster scenario, and you're trying to provide help, is like 7.5 to 10 liters. So that'd be sort of bare minimum for people to maybe wash their hands a couple times that day, to drink some water. Just as a reminder, this is 1 liter bottle, right? So if I were to drink this, and I tend to go through a couple of these, 2 or 3, maybe more per day. I drink a lot of water. So you could see, even just for drinking, it would be nice to have several liters, right? Let alone cooking, hand washing, all of that. So 30 liters per day would probably be a good minimum target, although perhaps it would be worth designing for more than that. Got that information in part from this table. This is the safewater.org. I think that's a Canadian NGO. They were citing the World Health Organization info, so I just grabbed that here real quick. they're saying, so the minimum kind of survival level, 3 to 4 liters for drinking, 2 to 3 for food prep, bare minimum. Add on to that some personal hygiene, maybe cleaning up after the food, and laundry, you're easily at 15 to 20 liters. So, we're not designing for showers every day and flushing here necessarily, although it might be really nice if that well is able to supply it, to set up for, maybe of the 8 people, 2 showers per day. I don't know if they're even going to use this for showering or not, or what they would do. Those would be pretty relevant questions to say, okay, more specifically, what have they been using this water for? Because what we'd like to do is treat all of the water that they're using. If nothing else, if we can't do anything better, maybe we just have a side stream where we treat some stuff that they're going to drink and cook with. So that'd be good, and maybe they're showering with dirty water, and that's better than showering with no water. But there's several layers to what's going on specifically for this community, right, or this family. So we'll kind of write a note here. So specific water use would be a question. And so part of the challenge here will be, I don't think we're going to design and build or lay out a plan for a week and a half from now for those of us that are traveling. But what we might do is set up a nice set of questions. Well, can we go interview them? Can we go go on the site visit and say, oh, hey, what's needed here? What are your specific uses? What's the deal here? Are you also feeding your animals or giving them water from this well? What does this look like in practice? There's a lot that could go into that. So we'll just kind of write a note that other observations and questions would be important. Last, I'd like to talk a little bit about our potential resources and limitations. So Brian was thinking, hey, can we do some sort of I think he said a biological sand filter, which is really, you might call it a slow sand filter. These were used a very long time ago as kind of a first line treatment, probably provides some benefit. It's kind of imitating groundwater in some sense. You've got your water, you're pouring it over a bunch of sand, and the bacteria that end up coating the sand particles are going to probably compete with other bacteria that might be more harmful, and hopefully munch on any nutrients and stuff that might be not great to drink. So you end up with water that is still biologically contaminated, but hopefully a little bit less so, and you end up with a situation where, if you run it properly, it's probably fairly self-sustaining. Whatever particulate matter and stuff accumulates will be food for the microbes that are living there. That's not, in my opinion, a great solution, and probably not the best solution in this particular scenario, but it's a good starting point. And I guess my question here, and sorry for the formatting, is I wonder if we could do, instead of a kind of a slow sand filter, maybe a more nowadays conventional sand filter where we call them today rapid sand filters, something like you'd see in a pool cleaning system. You have a cartridge that's got a bunch of sand in it, and you pour water through, and it's not so slow that you're letting biological activity do the treatment. It's the sand filtration itself, which might be actually what Brian was thinking of, or perhaps he was getting some mixed signals. I'm not quite sure. But he was looking for something that's essentially free, because they don't have resources dedicated for this project. Typically what they do is they will do a community scale project, not a home scale project. This is apparently one home, maybe it's in a pocket somewhere, and maybe it's maybe it's an Amigos employee, and they're like, hey, we'd like to have better water. Our community's not on board or something, but if we can do it, we'd love to. So I don't know the exact situation, and maybe there's a bit of funds there, or could be a bit of funds there. So the challenge for us, and I'll kind of open it up here in a moment, is, well, what can we do And what can we do on little amount of investment? What could we do with $100? What could we do with $500? Like, how long would that last? Like, what kind of a treatment would we come up with given these scenarios, right? So if we have pretty much zero, just some manual labor and access to some dirt or sand, maybe we can create our own sand filter, set it up, and get it running, right? That might be possible. One concept idea I have is my research works a lot with LEDs, and we actually have, and we brought one of these LED systems. They're designed for kind of home scale use where you have your piping and you want some extra treatment. Maybe you have a well that you're concerned about or something. And it's a pressurized system. You have water flowing in. It ends up mixing around in this little chamber with an LED it's got a reflective coating on it, I think, and an LED shining probably there or something, and illuminating that entire thing with ultraviolet light. And this is activated when water flows, and of course water is then going to flow out. So it's a pretty neat system, takes a bit of electricity, and it might be exactly what they would need there. So if we were to pair that with some sort of sand filter, we might be able to accomplish quite a lot for basically the cost of this thing. And as a research project, I could potentially say, hey, Brian, why don't you study this every month? We'll collect some data, make this a research project. They'll get some clean water out of it. We can't do that for everybody because I don't have the research funds for that. But since we have it, we might be able to have a win-win situation there and kind of trial that technology. So that's one thing that was on my mind. Maybe the one we have is not quite sufficient. I'm not sure, but it would be good to look at. So, okay, so that's the scheme, and that's my preliminary ideas about the scheme. How many of you would be interested in working on this project to some extent? Show of hands. Okay, some of you. All right. How many of you would be interested in having this as one of the presentation projects instead of participating in kind of the thematic, like groundwater issues, whatever? So of the people who just raised your hands, would you like that as kind of the way you? Yes, no, maybe? Impartial. I haven't given you enough information about what I'm expecting anyways for you to know, right? So it's kind of on me. Okay, so I will do some organization on that for you. I'll try to do so by Thursday so we can talk more about it. In the short term, if we've got some enthusiasm, I'd love to have people draft a couple concepts or draft maybe some sort of a checklist for, hey, what information do we need when we travel or when we do a site visit? And that's actually something very helpful that even if you're not going, you can contribute in the sense of like, hey, we need to know this. Like, how much electricity do they have? How much does that cost? Is that something they could afford to have an LED system? All sorts of questions like that could be very, very helpful to have and to bring. So I will post this itself, these slides, just for your info. I will also work towards making this into a more of an assignment. It's an open-ended assignment where anybody can contribute, and then as we move forward with, okay, here's your specific instructions on presentations for later in the semester, we can separate, say, okay, yeah, you're going to do this project. So we might have 4 presentations in total. So this being one group and so on. I'll work with you on that. I'll get better organization for you on that. But thank you for your flexibility there. Any questions or thoughts for now? You ever design a sand filter for anything? Any of you ever work with like a pool cleaning system, or some yes, some maybe? Any with like the sand filters, like the backwashing them and stuff? Nice. I actually haven't even done that, so that you probably have some good experience there. So something to that extent might be about right. Maybe we don't need quite as much volume there, but if we could make something like that, that could be pretty cool. Okay. All right, and turns out granular filtration will be pretty much the next topic, so that's a pretty nice nice lead-in. We left off last time talking about sedimentation, so we're going to wrap that up today. Let's see. I think the only other announcement I have at the moment is I'm checking in on the fee bill situation for the study abroad program. I still expect you shouldn't have to do anything with that, but I'm waiting to hear from them. It still should be paid by this other money, so not to worry, but I just need to figure out what they want us to do exactly. Okay, so we talked about sedimentation, how the fact that it's such an imprecise phenomenon that we kind of have to just check to see how it works, right? Kind of like doing the jar test to see, okay, the coagulant, how well is it working today, given whatever rainwater has changed the river today or something, you know. Sometimes coagulation, flocculation, you just need more or less coagulant, or perhaps a different type. So in the same type of scheme, our particles are going to vary, and their speeds of settling are going to vary. So typically what we'll do is make some sort of a column test to say, well, at what point have we settled enough for our process? So if we're aiming for 60% of the turbidity to be removed, you know, in this particular drawing, that would take 2 hours for that to happen, for 70% to reach that 2 meter mark. So anything above 2 meters, at least 70% of the turbidity has been removed. You know, and maybe there's a 100% line somewhere. So we can use things like that, and that gives us a way to, in some sense, categorize or sort the particles by size. Of course, they're changing and stuff, so it's not quite exactly, but that's maybe a simple way to explain it, and see how fast they're settling then. Okay, so another aspect that we didn't talk a lot about yet for causing coagulation, flocculation, is particle-particle bridging, specifically using some sort of polymer coagulants. So if we have these particles floating around, and we have, you know, they tend to have a negative surface charge, stabilizing themselves, well, maybe we have a polymer that has a positive charge on two ends. And so then what ends up happening is we have the positive meet the negative, and then we get the attachment, and now these two particles are bridged, and they're going to start acting in tandem. So it's going to kind of cause one larger particle in that sense. That'll tend to bring them close enough where then the other forces will take over, the van der Waals forces. And so you can imagine this is going to end up a lot like this fancy diagram that somebody drew. It looks like I drew it, but this wasn't me. You know, a squiggly mess of particles, right? And it's probably going to be like, I don't know, spaghetti and meatballs, right? Disentangling all of that is unlikely. So with gentle stirring, you're going to have more and more larger particles. So polymer coagulants can be pretty effective then. Oftentimes we'll use both ionic, so like alum or iron compounds, to facilitate the reduction of the electrical fields, but also add some polymers. So it's fairly common to do that, and that kind of gives us some potential examples of, well, how could we do this with natural substances? And that'll lead us to a particular substance, Moringa oleifera. Okay, so a couple other notes here. if you don't have a lot of particles, it can end up being not so efficient because, you know, if there's not a lot of particles to mingle with, then these polymers might just attach to the same particle. And yeah, maybe you have a little bit of an effect in terms of that's a slightly larger particle now that there's some polymer sticking to it, but it kind of has no effect, right? So that if you don't have many particles around, you can have a couple things that happen, maybe, and the other case would be overdosing the particles. So now you have too many of these polymers on one particle, and then you could actually kind of have a stabilizing effect just like that. If you get into some of surfactant chemistry and colloidal stuff, this actually looks a lot like what we call micelles. Actually, you might have also seen this in apparently some makeup remover uses surfactants, and so you might see micellar water. What that's referring to is when you have surfactants like soap molecules, which are kind of similar to polymers, and, you know, it'd be shorter, but what you're doing is you're encapsulating some particle with these surfactants, forming what we call a micelle that kind of stabilizes something that would otherwise not like to be in water. So if you're trying to remove makeup, for example, that's designed to be waterproof, well, it doesn't want to be in water, and so you give it an environment that looks that's coated, and you coat these particles with something that would be happy to stick to something that doesn't like to be in water, something hydrophobic, but it has a tail or a different end of it that's hydrophilic. So that's kind of what a surfactant often does, and then the micelles then would be these little, almost like a cell, it's a little bubble of stuff that's happy to touch, on the one hand, the hydrophobic substance, but then on the other end of the stick is happy to hang out in water. So that's a lot like that same thing, and you might end up having, if you overdose your system, you could have that situation. So even with soap, it's a little similar. Soap's not as effective if you have way too much soap. Let's say cleaning your laundry or dishes or whatever, it actually, the function doesn't do quite as well. Or too little, of course. Might also have an issue if you have too little dirt, you might not quite have the same soap action. Okay, so this natural coagulant, Moringa oleifera, that's the scientific name for this particular tree that produces seeds that we can extract and harvest. And this tree is actually quite common in a lot of different regions, tropical, semi-tropical, and a lot of the areas that currently still lack access to good water. So globally, it's present in a lot of places. And the deal is these seeds contain a lot of proteins that may be able to act like those positively charged polymers. So positively charged, we might say cationic. And these proteins, well, proteins are long molecules, large molecules composed of smaller subunits, so they're technically polymers. And so these proteins themselves are literally polymer coagulants if we want to use them that way. So you can extract them, grind them up. You might have to do some other processing. Maybe, I don't remember exactly, it might be boiling. But if you process them, grind them up, get them into a nice paste or powder like this, then you can actually treat water fairly well with it. So I've got a kind of an example problem that we can work through together. We're going to take a look. This is from our book. Kind of gives some description of precisely that. How do we use that? What would that look like? How would we design a use case and consider, well, how realistic is this? What would it take in order to accomplish this? Okay, so from our book, preparation of this solution. So we have to allow the seeds to mature and dry naturally to a brown color while still on the tree. Then we harvest the seed pods, remove them, shell them. Then we crush them and sieve them with a 0.8 millimeter mesh. So, that's probably like cheesecloth kind of stuff, something to take out the large chunks of shell or whatever's in there. The traditional large mortar and pestle is an appropriate method for crushing them if there's no mechanical alternative. So you can do it by hand if you need to. Maybe you have, I don't know, a coffee grinder or something that you could use, perhaps. Then you mix the seed powder with clean water to form a paste. It suggests 2 grams or 2 teaspoons of seed powder to treat 20 liters of water. As a rule of thumb, the powder from 1 seed kernel can treat 1 liter of very turbid water or 2 liters of somewhat turbid water. Okay, so when we crush them up, we need, let's see, about 1 seed kernel for this amount of water, right, if it's dirty. Okay, the paste, let's see. The paste should be freshly prepared for every treatment. Okay, so the freshness, these proteins are probably going to decay over time if we're not careful. Probably would respond to sunlight in that manner at high temperatures. So maybe you can prepare it today and use it tomorrow. I guess it'd be pretty obvious if it didn't work, but kind of having them fresh sort of matters. So maybe I would think that there's a good chance if you just collect the seeds and store the seeds in a cool, dry spot, that's probably fine. And then you do the processing. But there's some questions there of, can I only do this when the seeds are good? So potential limitations there, but it probably should be fine. Okay, so then there's a table here providing some NTU ranges. How much dose of your coagulant would you need, typically? Okay, so number 5 then is says dilute the paste in 1 cup of water in a sealed bottle, shake the solution. So basically kind of getting the mixture from the paste that you made into a bit of water that then you could dump in a larger thing of water. Filter the insoluble material either using a fine mesh screen or muslin cloth. The remaining solution is ready. It's now ready for use. Okay, so you're trying to purify it a bit, trying not to add contaminants when you're doing all of this, at least not large particles. So you get it ready, and then you're going to treat your water. So you pour the solution into the container with the water to be treated, stir rapidly for 2 minutes. So this is getting it mixed, and then you're going to go on to a gentle mixing, right? That's your stirring stage, and then you're going to stir slowly for 10 to 15 minutes. That's your flocculation stage, and then you're going to allow for sedimentation. So let the bucket sit for 1 to 2 hours. Do not disturb the bucket. This allows solid floc to settle. And then once they settle, carefully pour out the water from the top. Okay, so that's some instructions from our book from a paper in 2001. I think there's been ongoing research about how and why this works, so there's maybe some updates. I don't know about updates to the kind of conventional method here, but there's certainly interest in this because it's kind of a neat thing that can work. Okay, so let's take a look then at this example problem, and I'll give you a bit of time to work on this. We're doing well on time here. So when these seeds are used for treatment of a community water supply, thought should be given to the cultivation of seeds. Especially if we're treating a lot of water and continuously, we're going to need a lot of raw material, right? So it's kind of a problem that checks, is that possible? Is that reasonable? Or are we not? Are we thinking we can do more than we can? Okay, the average mature Moringa oleifera tree yields 3 kilograms of seed kernels per year. The trees should be planted with a spacing of 3 meters. Once trees are planted from seeds or cuttings, they grow rapidly up to 4 meters in height. Flowers and fruits are produced after 12 months. In locations with favorable climates, 2 harvests per year may be possible. As a rule of thumb, expect 3 to 5 metric tons of seeds per hectare per year. Okay, so I did a lot of calculations there for you. It was giving you all this information. but then it just gave you some amount of seeds per year per area. So it gave you the information you may be able to calculate, but then it kind of did a lot of that for you. But if you do think about it physically, spacing trees every 3 meters, that's about every 10 feet. You can imagine what that might look like, kind of like an, apple orchard or something, right? You could envision doing this on purpose to try to grow your seeds for coagulation. At some point, you might think to yourself, well, we're going through all this effort. Why don't we just buy some alum? So not saying that's the right answer, but as we scale this up, it's worth considering is, the cost of scale up compared to what else we need. Okay, so this example provides calculation for determining the land requirement for drinking water with Moringa seeds. So it says calculate the required land area to treat water with a turbidity of 150 NTU with a process flow rate of 10 cubic meters per hour that operates 8 hours per day for 1 year. I'm going to flip back for a moment so I can write on here the milligrams per liter dose that is suggested for 150 NTU. And then I'll give you some time on this. So the dose range was 50 to 200. An answer or close? Okay, so this is a excuse me. This is a pretty good example of the type of problem I might put on the final exam in terms of the calculation here shouldn't really be too specific to something we learned exactly, but it's the context, and like then I might follow up. Well, what are your thoughts on the practicality here? Maybe I would add in some economics sort of a assessment, like how would this compare if purchasing alum costs this amount? What are the factors you think might be at play there? So what I'm aiming for in general, just to give you a better understanding of that, is that you are thinking critically across different dimensions here, right? Is it reasonable that you plant an orchard of Moringa, right? Is that a good approach, or what costs might be associated with trying to do that? Okay, so let's take a specific look at how the book did this, and essentially we're going to take. They decided it looks like 100 milligrams per liter, and this is certainly a little bit arbitrary. We were given a range of 50 to 200 milligrams per liter of our Moringa extract, given the condition of over 150 NTU. If we take a skip back just a second, we see this range, two ranges actually given. One was above 150 and one was 50 to 150. So the upper range of this seems like what they selected, but you could have also selected 50. Or maybe you make a guess and say, well, on average, maybe it's something like 100, but it should probably not be so dirty as to require 200 all the time, right? So some sort of thought process like that would have been good to think about. But if you had assumed 50 milligrams per liter is sufficient, that's fine. You can go with your calculations on that, right? Whatever, and in this case, the book solution is assuming 100, so we're going to carry forward with that. Okay, so then we're going to convert that into kilograms so that we can kind of relate the units. We also know that we need to treat 10 cubic meters of water per hour, and they're going to convert the cubic meters into liters, so we're going to multiply that by 1,000 liters per cubic meter. And then every day, you're only treating for 8 hours. So you have 8 hours per day, and that'll convert your units here into per day units. Normally we do 24 hours per day, but that's continuous operation, right? In this case, we're only 8 hours in the day, only a third of the day. Okay, then we can convert that into years, 365 days per year, and then we get some amount of kilograms per seed, and then we can go and say, well, how many hectares is required to produce that many seeds every year? And so we can go back and look at their calculation. So it's really a matter of following the units and doing a few conversions. And they come out with a 0.97 hectares, so about a hectare of land for that. Does anybody happen to remember what a hectare is in maybe our non-SI units? 2 to 3 acres. Okay. 10,000 square meters. Okay. Yeah. Great. Okay, so a decent plot of land. Okay. All right, so that's the answer there, and let's see, what size of community was that? Did it say? No, but 10 cubic meters per hour so 80 cubic meters per day. That's a pretty good amount of water, right? That's a sizable amount. So that's definitely more than the scale of a household or two, right? We were talking about, in our other slides, maybe something like 30 liters per day per person times 8. That's 240 liters per day for that well system. 250 liters per day, something like that. This is quite a bit larger. So it's interesting to think about doing a full-scale system like that. It may actually be possible. But also think about the amount of labor going into it, preparing fresh moringa seeds every day, right? That's actually a pretty big cost, right? Labor cost here would be large if we're extracting, let's say 2,900 kilograms of seeds every year. We could do that calculation, but how many is that every day? And we're supposed to prepare this fresh every day? Okay, how many people are we employing for how many hours every day to do a repetitive task in order to make this work, right? There's a big question there about that side of the cost. So it is really neat that we can use them, and that would be a sustainable water treatment plan. Sustainable in the sense of locally sourced natural stuff. But there are some other questions, are these proteins safe to drink? There are some important caveats there that ought also to have some attention. Okay, if you're interested in a recent article, this is my postdoc advisor, Vlad Tarabera. He's been working on this, and last time I taught the class, he had just published this article when we were talking about it. So this particular article is for water treatment, so the flock structure, residual organics, and performance trade-offs. So it goes into exactly that type of stuff. Definitely recommend it. I think I probably posted this on Moodle. I would probably need to activate it, so I'll check in on that to see if I have that paper up for you. But it's a good read. If this is an interesting topic for you in particular, that would be a good resource. So take a look and see about that. Okay, last thing I wanted to say for coagulation, flocculation. I mentioned these Procter & Gamble's water purifier packets. I think they used to be called Pure packets, P-U-R. But I was able to find them on Amazon and elsewhere as purifier of water, portable emergency water filter purifiers things. Essentially, these are little packets. They have a coagulant in them. So you pour it in a 10-liter bucket of water. You stir for some amount of time. You let it settle, and then you're going to strain it off. And the deal here is it's not just the coagulation. They're also, I think, have chlorine or some other chemical disinfectant powder in there. So when you add it all together, you are getting all of the above, both sedimentation and disinfection. So it's a pretty neat option. You can see this water they're starting with, and it can clean it up quite well. And presumably that would be safe to drink, or safe enough, right? There's a few concerns. Some pathogens, Cryptosporidium and Giardia, they can form cysts that could persist and be kind of immune to that amount of chlorine. Fortunately, they'd be a little more likely than other pathogens to be caught up during the coagulation, but might not happen. So there's probably still a little bit of risk, but it's just so largely reduced compared to what you would have otherwise, right? So it's quite a good treatment, a potential opportunity, right? So that's pretty neat. I think they calculate, Amazon's probably not the right way to calculate it, but I think it turns out to be less than $1 per packet, and you can treat 10 liters with that. So it's like you can treat water for a fair number of people using these, pretty low cost. Okay. The only other thing I wanted to say today is I got an email while you were doing that assignment about the program fee for the study abroad. The person helping me says, I don't think they've been assessed a fee. They're probably referring to the waiver that they have to sign that says everything they've paid is non-refundable after March 1st. Since they're not paying, that deadline doesn't mean much for the program. So Uh, okay, I'll email her back and let her know that. Okay, thank you. So we'll get on that. If there's something to sign that says it's non-refundable, that should be safe to sign. But if they're charging you money, yeah, we'll figure that out. Okay, so for Thursday, make sure to do that participation. I will plan to have some more specifics about project presentations, and next Thursday we'll have sort of a guest appearance from those working in Nicaragua to join us for class for a bit. All right, so with that, we'll see you on Thursday.